Hello, these are the answers to page 6, Forces in Motion. So make sure you correct your work, and remember your new teacher next year is going to have a look at these booklets for you, so it'd be great to see your work corrected in them. So we're looking at a distance time. So if we look at this first graph, distance time graph, we've got the different sections, and the question says describe the motion described by this distance time graph in as much detail as you can, and use the numbers off the graph. So what I would do is sort of talk about each section separately. So it's on a distance time graph. So if we talk about A to B, what A to B is a straight line with a positive gradient that doesn't change. So a straight line on a distance time graph tells us that we have a constant velocity, okay? And we're able to work out that velocity because velocity is change in displacement or distance over time. So what we can do is we can figure out the distance travelled at the velocity by doing the distance travelled. So B it's at 40 and at A it's at 0. So we do 40 minus 0 over the time, which is 3. So that gives us a velocity of 13 meters per second. Okay? Then we're looking at B to C. Now B to C, the line is flat, and actually B to D, in fact, so C to D, both of those, the line is flat. So that means that the object would be stationary. Okay, so our velocity is 0 meters per second. D to E, we again have a positive gradient, so we're going to move forward at a constant velocity. And that velocity will be the change in displacement, so that's 80 take away 40 divided by the time that took, so that is 11 take away 9, which gives us 40 over 2, which is 20 meters per second. Okay. And then E to F, the line is flat again, so again E to F is stationary. Some of you might be wondering why I'm writing meters per second like this, so I'm just going to explain that to you. You're probably used to writing meters per second like that. And the reason we write our units as like that is because speed is distance divided by time, so we're doing meters divided by seconds. So technically what we're doing is this. And when we have a number underneath the line like that, how you can write that instead is s to the minus 1. So that minus 1 to the s means it's meters divided by seconds. So from now on at A level, that's how we'll write things like that. So I'll show you the one for acceleration in a minute. So that's describing our distance time graph. Let's look at our speed or velocity time graph. Okay, it should really be velocity time graph rather than speed. So I'll move this a little bit. Okay. So again, we've got our sections, and we're going to use the numbers to describe the motion. So if we look at section A to B, a positive gradient on a velocity time graph tells us that we have constant acceleration. And our equation for acceleration is change in velocity divided by time. Change in velocity divided by time. So if we look at A to B, our change in velocity, it goes from 0 to 30. So our change in velocity is 30 minus 0, and our time is 3 seconds. So our acceleration will be 30 divided by 3, which is 10 meters per second squared. And what you can see here is that that is the same as writing meters per second squared, like so. Okay? B to C is a flat line, and on a velocity time graph that tells us there's a constant velocity, so it's not changing from 30 meters per second. From C to D we have a straight line again, increasing, so we have constant acceleration again. And we can work out values here, so it goes from 30 to 70, so 70 minus 30 will tell us the change in velocity, and the time is 9 minus 6. So we've got 40 divided by 3, which gives us 13 meters per second squared. Then E to F, okay, the car is at 0 meters per second, so the car has stopped. So our velocity is 0 meters per second. So that's how you calculate the acceleration from the gradient of the graph, okay? What you can actually do is work out the area under the graph as well, and that tells us something different. So the area tells us the displacement. So what we're going to do is split this up into sections. So I've got my A to B, B to C, I've got C to D. I'm going to make this into sort of 2 sections. And then I've got my last section, which is D to E. And if you work out the area of each of these sections, it will tell you the displacement of the car during those sections, okay, or the distance travelled. So let's do distance travelled first. For A to B. So what we have at A to B is a triangle. So the equation we're going to use for that is half base times height. So this is a triangle here, so we're going to use half base times height. So the distance is going to be 0.5 times the base, which is 3, times the height, which is 30. And that gives me a distance of 45 metres. Now we're going to do B to C. B to C is a square, so we just do base times height. So we've got 1, 2, 3 times the height, which is 30. 3 times 30 is 90 metres. Now, the next section, this isn't a trapezium, and I always forget how to figure out the area of a trapezium. I think it's half A plus B times the base, but I can't remember. So what I do is I separate it into a triangle and a square. So I'm going to do the triangle first. So I've got half times 1, 2, 3, 3 times the height, which is 10, 20, 30, 40. And that equals 60 metres. And then I've got my square here, so that's 3 times 30, which gives me my 90 metres. So those two go together. That's for C to D, okay? And then I've got my last section, which is this triangle here, D to E. So D to E, the distance is a half times the base, which is 1, 2, 3, times the height, which is 70. And that distance there is 105 metres. So what we can do then is work out the total distance by adding them all up together, and that gives me a total distance of 390 metres. So that is how far the car has travelled, okay? Its distance or its displacement. E to F, it doesn't cover any distance because it is at a 0 velocity. Okay, mark your answers, add any bits you've not done, okay, and then you can get on with today's lesson, which is waves, please. It's page 7. Thank you.